Electrical systems are covered in ATA Chapter 24. And when we're looking at transport aircraft systems, we're going to primarily be looking at alternating current. You covered DC systems and DC electrical systems when you had your basic systems course. We'll talk a little bit about DC. There are DC systems on there, but the primary power source on most transport aircraft are going to be AC. Okay, my thing did not like that for some reason. Right again. There we go. So things we'll cover: primary and auxiliary power generation for the AC systems, including devices called integrated drive generators, which are made up of a constant speed drive and an AC generator. We have to look at ground power, which is typically fed as an AC ground power. How the power moves around, distribution buses and that kind of thing. Then from those buses, that's the main power backbone, and then distribution panels, circuit breaker panels that actually send power to the individual components, subsystems, devices, and that kind of thing. Emergency AC power generation, and then we'll look at the DC electrical systems, which on transport aircraft typically rely on AC. They take AC and rectify it for DC use, but they do have backup systems, in case of emergencies or loss of power. So the layout diagram you can see there kind of shows where the main power sources and buses are located on a typical transport aircraft. So on this aircraft, you can see we have two engines are going to be where we generate most of our power. We also have an APU that typically can generate power. Somewhere we're going to have what's called an E&E bay, electrical and equipment bay, or an avionics bay that has most of our primary power distribution. Newer aircraft, that's almost always under the floor. Older aircraft, some of them did have it up in panels located in the cabin, but they've tried to move as much of that out of the cabin as possible for safety's sake. And then going out to the various loads around the aircraft. Schematics are a big part of understanding these systems. And so here we have a schematic of an electrical system for a transport aircraft. So there's this kind of basic diagram. This is showing a lot of the same things. But if we start to take these different areas and components and put them together, you get something that looks like this. So to break it down, we have our sources in this case along the top. There's those two engines and our APU generator, just like you show here. Two engines, left and right, and our APU generator in the tail. Here are our two main sources, the two engines, plus an auxiliary source in the form of the auxiliary power unit, the APU. Those feed into various buses and switches that move the power where it needs to go. Okay, they're the buses. So we have various switches and contactors that are going to direct that electrical power to the appropriate buses. And the buses, again, are kind of the main, we'll call it the main artery of the system. It's where everything else taps off of. We're going to have some kind of redundancy and backup, and that's shown on the right side here. This is an emergency system that uses something called an ADG, an air-driven generator. One of these pops out, you're not having a great day. And then the bottom half of the drawing, we take that AC and we create DC using transformer rectifiers. And the system, though, the way the DC system works is very similar architecture. We're still going to use things like contactors and different switching elements to feed buses that ultimately are going to feed users of the electrical. So transport aircraft systems, primarily, most of them run on AC. There are a few smaller transport aircraft, and when I mean smaller, I'm talking like 50-seat jets, the Embraer 135, 145, 155 family. That is a DC aircraft. Some of your corporate jets are DC as well. Things like Cessna Citations, most of those are DC. Learjets, mostly DC. But when you start getting into bigger, There are also like the Canadair CRJ regional jets. Those are AC, even though they're 50 passengers as well. They're an AC aircraft. And pretty much anything be larger than that, more than 50 seats, is AC. And in the corporate world, when you get into something like a Challenger or a Global, those are AC aircraft. Falcons are a mix. Some are DC, some are AC. Depends on the size. Typically smaller DC, bigger AC. A lot of your turboprops are going to be DC just because they use a starter generator type system. But primary AC systems, the most common you'll see out there is 115 volt AC, 400 hertz, three phase. And that means going to any device that uses all the phases, you're going to have three power wires plus a ground wire. Three phase wires plus a ground. Now, some devices can use a single phase, can run off a single phase. Higher power devices will run off all three phases. But ultimately, why do we use this instead of DC? Why do we put this complication of alternating currents and all the funky things that go with it? How many people liked AC when you had electrical class? I'm seeing thumbs down. No, yeah. So it's more complicated when you look at it from the theory standpoint. Fortunately, the wires and how they all go together look pretty much the same from the outside. So why AC instead of DC? Anyone, any ideas? So these are a higher voltage, and you're going to get less voltage drop over a longer distance with AC. So hence, bigger aircraft, it's important to be able to have that. And because you have less voltage drop, you can have lighter and smaller wires and components and greater power for a given size component as well. At the end of the day, the big thing we're trying to do in an airplane is we want it to be safe, number one, and two is we need it to be lightweight. Right? Weight equals efficiency equals fuel. And so AC systems, because they're more efficient at moving power, they're able to make the components smaller for a more powerful system, and thus it's going to save weight and make the airplane more efficient. Newer aircraft, some of the newest aircraft, use 115 volt, 235 volt, variable frequency three-phase. So it's still a three-phase system. They're an even higher voltage for many of the sources. And we use a variable frequency. So first off, why do we go to the higher voltage? Kind of touches on what I just talked about. Higher voltage means what? Where is voltage important? You guys didn't have you slept in electrical class? What's the effect on voltage when we start talking about what are we trying to get out of electrical? What is electrical doing? Power. Okay. Oh, I grabbed my one like crappy marker. So power, let's see. Power equals what? Yep, voltage times amperage, or current times voltage. Power equals current times voltage, PIE. E is another term for voltage, okay? That's how I remember it, it spells pi. Power equals current times voltage. So we need more power, or we need the same amount of power, right? Bigger airplanes need more power. So we can do two things. If we need more power, we can either increase the current or we can increase the voltage. If we increase the current, what do we have to do? We have to make our wires bigger. And, well, to prevent the heat from causing a problem, you have to increase wire size to deal with the added temperature, the added heat that it could produce, well, or to prevent the heat from building up in the first place. So what is the problem with bigger wires? More weight, right? So now we want to get more power out of our system. We don't want to increase the weight, so we're going to keep that where it is. That means we have to increase the voltage. Okay? So newer aircraft that have higher power requirements have gone to these 235 volt systems. The big example of this is the Boeing 787. 787 went to a no bleed architecture. What I mean by no bleed is older airplanes, pretty much everything but the 787 at this point, take hot air off the engines, and they use that. The main thing is to de-ice the wings. You pump hot air into the wings, you heat the wings up, it prevents ice from forming. The 787 uses electrically heated wings rather than bleed air. And so they needed more power in order to do that. Same thing. The other thing you can do is you increase that voltage, you get more power, you can use a smaller hydraulic pump, right? So rather than getting more power, you get the same amount of power from a smaller package, right? So it allows you to use smaller components. And the other part of that is like control systems, right? Things are miniaturized, computerization is made, you know, controls and the ability to work with it a lot smaller, right? Computers used to fit in a giant room, and now they fit in a watch on your wrist, right? Or a little slab of glass in your pocket. There are ones, yeah. So advantages, so that's one advantage. The other part, variable frequency. Anyone have any idea why variable? I know I put it up for a second, but hopefully you didn't see it too bad. What generates our power? What did I say generates power? A generator driven by what? By an engine, okay? What determines the frequency out of a generator? How fast it's spinning, or RPM. So if we want to keep that frequency constant, like we have here, 150 volt, 400 hertz, we got to keep that generator moving constantly, and but it's driven by an engine that's variable, right? Takeoff, it's going really fast. Climb, it's still going pretty fast. Cruise, it's slowed down a little bit. Descent, it's really slowed down. So now we got to add some kind of device to keep that generator going a constant speed. It's known as a constant speed drive. So if we can deal with variable frequency, what's the advantage? We don't have to worry about constant speed drive. What do you think that constant speed drive is? More weight. The one on the 727, the constant speed drive, probably weighs somewhere around 70 or 80 pounds apiece. They are massive. And that's not the generator, that's just the constant speed drive portion of it. So if you can get rid of that, you can save weight. So advantages of variable frequency, simpler and lighter generators. And so the A350, A380, 787, the Bombardier Global, they've gone to what's called a wild frequency architecture. And for most of your components, frequency doesn't matter that much. If you're heating a leading edge of a wing, doesn't matter what the frequency is. Not really. You just run current through a resistor and you get heat. Trick question. If you're heating water in a coffee maker, does frequency matter? Those of you that had class yesterday will say yes. The rest of you will probably say no. One of the weirdest troubleshooting things I ever had was troubleshooting a coffee maker because it didn't like the frequency going into it, even though all it has to do is heat up and make water hot. But different story, different day. What we've done is everything that can run off wild frequency in these aircraft now does run off wild frequency. What would need a specific frequency potentially? What might need a specific frequency? Things that are more sensitive electronics, things like computers. And so what you can do though is now we have these really nifty solid state devices where before this used to have to be done with a mechanical drive and all that. That can be done in this tiny little chip inside of an individual component. You know, maybe you need 100 of those chips in the whole airplane. And altogether, those 100 chips weigh a couple pounds. It's still a lot less than one 80-pound constant speed drive. So for the components that need a fixed frequency, we put in something that can take in a wild frequency and puts out a constant frequency and does it in a solid state manner rather than using a mechanical drive. So solid state switching circuitry is used in order to provide that constant frequency for something where it's important, and for everything else we say we don't care if it's running at 400 hertz right now and if it's running at 300 hertz on descent and if it's running at 600 hertz during takeoff and climb. The other half of the electrical systems, DC is typically used for backup, standby, or secondary, with the exception of there are some avionics that do require DC. Okay? And DC can be its own system, or in some cases, things plug into the AC system, and then they have their own transformer rectifier in them to create DC for their use. That's what the charger is on your laptop. That's what the charger is for your cell phone. That little power block that plugs in, this thing right here is a little transformer rectifier. USB port on one side, plug on the other. This takes, in a house, in a building, 120 volt, 60 hertz AC goes in, 5 volts DC comes out. So you could build something like this into components on the aircraft, and this thing weighs a matter of an ounce, right? So we can build those in. So DC, though, does have some advantages. Like I said, small regional jets and turboprops use DC rather than AC because of the starter generator setup. It's still 28 volt like you've seen on general aviation, smaller aircraft. But the big advantage of DC is it can be stored and allows for simpler backups. How do we store DC? In a battery. How do we store AC? You don't. There is no AC battery. You have to generate it. Spin up a flywheel and use it to turn a generator or something. But that's not storing the actual AC, that's storing mechanical energy and converting it. Okay. So if we look at it, do a simple block diagram. These are the schematics that I like. Everyone's gonna, by the end of the semester, if you hear the word schematic, you're gonna wanna like punch somebody. So here's a schematic. This is a block diagram. It's a form of schematic. So we have our AC generation feeds into AC distribution. Okay, and components hooked to that. Then we have DC generation through a transformer rectifier, or transformer rectifier unit. That's what TRU stands for. DC distribution, and then we've got our DC generation / storage in the form of batteries. Probably the most simple electrical diagram of a transport aircraft you can create. Okay. When you guys do yours, they're going to be a little more complicated. We're going to look into it in a little more detail, but here is the simplest electrical system for a transport aircraft you'll probably ever see. So it's an easy topic, right? That's all you got to remember. No, there's more to it. Okay. AC versus DC. I just talked about this, power, current times volts. You know, here's an example with a 12 volt system. If you want a power of 100 watts, it's going to draw 8.33 amps. You need a pretty good size wire for 8.33 amps. If we use 120 volt AC, we can get down to 0.833 amps. Right? Big difference there. Now, another aircraft would probably be 24 volt system, so this would be 4.16 amps or so. Right? But still, 4.16 is a pretty good current draw. You still need a pretty sizable wire for something like that. So there's two main theories of design that are used in the type of bus architecture. There's two bus architectures. Ultimately, we're going for today what's called a fault-tolerant design. So older aircraft, and this is our 727 is an example of this, had all of the main buses connected all the time to each other and to each generator. So the 727, for instance, has 3 generators. It has 3 main buses. Those 3 main buses are all connected. I'll show you that in a minute. So when they're connected all the time like that, it's referred to as a parallel bus. Newer aircraft, most newer aircraft, the buses are isolated unless they need to be connected. Say in the event of a failure of a generator. So one generator powers one bus, a second generator powers a second bus, and under normal operation, they are separate from one another. But if a generator fails, they can be connected. And the idea behind this is by being fault tolerant is if you have a problem, so you have a surge or an overcurrent or something of that nature, if everything's connected, you have the risk of that surge affecting everything that's connected together. Okay. However, if it's isolated, the chances of a single failure taking out every electrical system on the aircraft is lower. But what you have to be able to do is quickly power something back up if there is a fault where you lose power to a single bus. Okay? The other part of that is distributed load. When we have those multiple buses, we don't want to have a whole bunch of stuff all powering off of bus A and almost nothing powering off bus B when they're both driven by two equal engine generators. So we have to distribute our load, our electrical load, in a manner that's going to make sure that's the case. The other thing we have to do is if for some reason those all do have to be combined, because say we lose an engine, we have to be able to match the resulting combined load with the generator that's operating, and that's called load shedding. We have to get rid of things that maybe aren't as important. We'll talk about how that works. But this creates a redundant system that allows the aircraft to operate, to be incredibly safe. It's very, very rare the plane loses power. So let's look at how these look. So here is that parallel bus system. This is a simple block diagram schematic of the 727. So here I'm going to focus, go back. This is the AC and DC. Right now we're going to focus on the AC system, which is the bottom half of this diagram. You can see, just looking at it, we've got 3 generators. We have an APU generator. It's working from the bottom up. 3 AC buses. We have what's called a sync bus. We'll talk about what that's for. An essential bus. What do you think essential bus is for? Essential items, those things that are really important. Right? You can see that's powered off of the sync bus. We've got a plug over here to the right for external power. So here is the ground power configuration. So when we're operating, say, the 727 here on the ground, this is what our bus architecture is going to look like. We're going to feed power in over here to the right. We're going to put power on this sync bus. And from there, power is going to flow through these boxes that aren't highlighted but have the line through them. It's BTB, stands for bus tie breaker. It ties the buses together. It serves as it's a contactor and a circuit breaker, so it can be turned on and off, but also if there's an overcurrent, it will trip. If there's an overcurrent on AC bus 2, hopefully this will trip so that it doesn't overcurrent the rest of the system, right? This is that fault tolerant design. This is the older version of it, but bus tie breaker. Okay. And then you can see our AC essential bus gets power from bus 3 over there. Okay. But what can happen is those bus tie breakers can be opened once our power sources are on. And the generators, as they're turned on, initially are going to power their individual buses. Okay? But the breakers are open right now. Bus tie breakers are open. This is not yet parallel. This is actually kind of how a more modern split bus system works. Okay? However, on the 727, you don't leave it this way. Once you have your generators on, you parallel them. And so what that means is the flight engineer would, one at a time, they had gauges that showed the frequency of this sync bus and the frequency of this generator, and they could adjust the kind of an input into the generator speed drive to get the frequencies to match. And once they matched, they would close that bus tie breaker and it would lock these together. When you have AC generators, when you start paralleling them with either the power card or with each other, when you get the frequencies close and you connect them together, they actually electrically lock into each other. Remember, an electrical current through a coil, which our generators have a bunch of coils, right, creates a force. And that electromotive force will actually lock those generators together. Even if one's being driven slightly faster or slower than the other, the faster generator will actually kind of push the slower generator to go faster. Or the slower generator will kind of put some drag on the faster generator to go slower so they stay at the same speed and in sync with one another. But you got to get them close before you try to hook them up. So these have to be manually paralleled. So they would parallel 1, hook it to the sync bus. Parallel bus 2, generator 2, and then connect it with the sync bus. This would all be done on the ground before they flew. Parallel generator 3, reconnect it to the sync bus, and at that point, all 3 would be locked together for the duration of the flight. putting out the same frequency. If there was a failure on a bus or with an overcurrent, for instance, the bus tie breaker, if say the generator failed, now bus 2 is still powered off the sync bus. Okay, instead of just locking them together, normally the sync bus in this situation, all it's really doing is locking them together. It's also doing some of that load sharing. If there's a little bit bigger load on bus 1, a little bit less on bus 2, some of that current's going to flow over to bus 1. Okay, so they all will have an equal load on them. But if suddenly we lose Gen 2, now buses 1 and 3 will send current through the sync bus and continue to power AC bus 2. GB at the bottom there is generator breaker, by the way. That's what connects and disconnects a generator from a given bus. You can even lose 2 generators and still power everything. Now you might have to shut off some devices that are connected to those buses so that you don't try to take too much current from one generator. One generator can't necessarily power the entire airplane, but maybe you shut off some of those non-essential things. You don't need the coffee makers to make coffee if you're down to 1 out of 3 generators. The 727 doesn't have it, but today you don't need the in-flight entertainment system if you're down to a single generator. You maybe don't even need the main cabin lights. You can switch to just some emergency lighting. Maybe you don't need all the displays in the cockpit. You can shut off displays. Now, the nice part today, everything going to LED and flat panel displays, they don't really use that much power. But you might shut down certain things in order to reduce the load. That's called load shedding. When we're on the ground, we switch to our secondary source, our APU, power it up, close the generator breaker, and then they can shut off all the generators, shut down the engines, which shuts down the engine-driven generators. And now you can power the aircraft off the APU. So you can see there's all kinds of different configurations that this parallel bus system can operate under. The one we'll be operating under for lab is this one right here. We'll be feeding power in through the external power receptacle. We'll be putting power on the sync bus, and that power will be going to the individual AC buses. We will not be running enough on the plane at any given time that will be at risk of overcurrent, pulling more current than what the power cart can handle. At any given time, we may be running a couple hydraulic pumps. Those are some big current draw. We might be running a fuel pump or 2. That's a somewhat sizable fuel draw, though it's not huge. Maybe some lights sometimes. Honestly, the landing lights are a big current draw, big old school, light bulbs that when you stand in front of them, you get a suntan and you can feel the heat coming off of them. Very inefficient. But for the most part, we'll be able to run all 3 buses without any kind of an issue for what we're going to do. It's only once the plane's in full flight configuration with everything running simultaneously that you start to have to load shed. But we're only going to run one system typically at a time. So that is the older method. Newer aircraft, we saw this diagram already, use what's called a split bus. And that the term comes from the parallel bus system. Normally the buses and the generators and the frequencies are all in parallel all the time. The frequencies being matched up is parallel. Split bus comes from the fact that the buses are not connected during normal operation. They can be in abnormal situations. They can be for the ground, like ground power or APU power. But when the airplane's in flight, when we say normal configuration on pretty much any airplane is in flight, in cruise. Flaps up, gear up, all that. Anything outside of that is either some kind of a special case, landing configuration, takeoff configuration, or some kind of an abnormal configuration. But here's the electrical system architecture for another split bus aircraft, the A319, 20, and 21. It's an Airbus. Here's another one. That's the 787. Now remember, this is a wild frequency airplane, but it still uses a split bus system. Okay. And if you take time to study these, you'll see that they're really not all that different as we go through them. Drawings are made differently. Newer airplanes have fancier color drawings instead of black and white. So this is, that's a CRJ, that's the A319, that's the Boeing 787. The biggest difference you'll see here is, my clicker died. The biggest difference you'll see here, go back, is that you have one generator per engine on the regional jet, one generator per engine down here on the A320, APU generator, emergency. 787 actually has two generators on the left engine and two generators on the right engine. Remember, it's a power hog. It uses electrical power for a lot of stuff that used to be done pneumatically. So they put a lot of generators on it. So if we look at this more closely, see how it operates. During normal configuration, we look something like this. And if you follow this diagram from the left engine, mechanical rotation powering our constant speed drive, mechanical rotation powering our generator, converts mechanical rotation into electrical energy, electrical potential, flows through these various contactors down to the bus one. You can see bus one here is powering our AC utility bus one, our AC essential bus, but it's not connected to generator two, AC bus two. There's a definite split down the middle between the left and right side. So here's where that split bus comes through. This is normal in-flight configuration. Both engines are working, everything is, planes cruising along, pilots are drinking coffee, taking naps, watching movies on their iPad, right? But if suddenly we lose an engine, it has the ability through these various contactors, generator transfer contactors, to now use generator one to power both sides, for instance. Here we are powering the left and the right, or bus one and bus two off of the left engine, the left generator. And this little, you see these little boxes next to the generator, GCU1, GCU2, that stands for generator control unit. That's the little, essentially, computer that controls, that helps to control the generator. Or in a 727, that was the job of a flight engineer. But, it's moved, these contactors have moved, plane, and in this configuration, this plane can actually fly on, whether it's an engine, whether the right engine had to shut down, or that right generator went bad, or the right generator control unit went bad and can't control the generator, the constant speed drive, had a problem with, it stripped gears or something like that. Doesn't really matter. Plane can still operate. And here it hasn't shed anything yet. Some airplanes, this one in particular, can operate everything off of a single generator because it's a smaller plane, a 50-passenger airplane. When you get into bigger aircraft, they're going to have to shed some of the non-essential stuff when things go bad. You can run everything off of an auxiliary power unit with an APU generator. You can see that kind of can do the same thing. So generator run off of a little turbine engine back in the tail. Works for use on the ground. It's a backup in the air. Okay. Or if things really go bad, we have something called a air-driven generator, ram air turbine. We've lost both engines, we've lost our APU, a little turbine propeller flips out of the side of the airplane, starts spinning in the airstream, and it powers a small generator. That generator basically powers the essential equipment. On this airplane, that's one hydraulic pump out of 6, which is enough to be able to run the flight controls. On a transport aircraft, you cannot run the flight controls without hydraulic power. There is no direct connection, physical connection between the yoke and the flight controls, or the rudder pedals and the rudder. You have to have hydraulics. So it runs, in this case, one hydraulic pump. I think 2 displays in the cockpit out of 6. And the emergency radio and like an emergency navigation instrument. That's about it. Because all it is a little propeller spinning. The main generators are about that big around and are about that long. The little ADG is about that big around and about that long. So can't put out nearly as much power, but it's enough to glide the airplane, to maintain control, to glide the airplane to the ground. 727 uses a battery backup. We'll look at that when we get to DC power. This is an AC generator. Okay, so it's a backup on the AC side. A couple airplanes out there have kind of a hybrid of the two systems. And this is the 747, for instance, uses a split parallel. What that means is this is a 4-engine aircraft, 2 in the left wing, 2 on the right wing. It has 4 main generators. It has 4 main buses, but under normal operation, under normal operation, the way this works is generators 1 and 2 power buses 1 and 2, and they are normally linked together. And generators 3 and 4, which are the right 2 engines, power AC buses 3 and 4. They're linked together through a sync bus, but normally 1 and 2 together are not connected to 3 and 4 in flight. So that's where the term split parallel comes from. Not very common, just a few large aircraft that did this. Okay? It's a split parallel because essentially you're running as a parallel bus on the left, a parallel bus on the right. They're split under normal conditions. If for some reason you lose both generators on one side, then you can connect the entire thing to power all 4 generators off of, the 2 generators, all 4 buses off the 2 generators that are on the opposite side. Not going to go through the full operation of this, but things can be moved around. Essential buses. There is this one's kind of unique. It's got Gen 5 right here. It's powered by a hydraulic system. So a hydraulic system uses pressure to spin a hydraulic motor that turns a generator. Okay. So kind of a backup. And I can't remember if the green hydraulic system on the 747, I don't remember exactly how that one's driven. If it's either directly driven off of one of the engines, or it has a pneumatic pump on it. I'd have to look at the hydraulic schematics. So. With all of these, we'll go into it. With all of these, we have to be able to control our electrical systems. And so we're going to have some kind of a control panel in the flight deck. Maybe counterintuitive, maybe not, because you know about this, but the older the airplane, the more complicated the controls in the flight deck. So on the 727 out there, you have an entire fairly sizable section of the flight engineer panel that is devoted to electrical system control. On most of your new aircraft, it's a panel about this big over the pilot's heads, with just a few buttons, knobs, or switches on it. Because functions that were done, by the flight engineer on older aircraft, that's been done by a computer. Most of the management on electrical systems on a modern airplane, during the course of normal operation, the pilots don't even touch the control panel. It uses computer automatic management to run all normal operations. This panel, for instance, you can see generator 1 and generator 2. There's an auto position, an off position, and a disconnect. 99.99% of the time, this is left in auto, and the pilots don't even touch it. During their checklist, they look up, yep, auto, auto, and that's it. They don't even move it to the off position. The off position is only if you have to shut it off because of a problem. When the engines are running, the generator comes on, automatically starts powering its respective bus. When the engine shuts down, the generator stops spinning, it stops putting out power, the generator turns off. You don't actually have to turn it off. You restart the engine, computer senses the generator's up to proper speed, it makes the generator put out power. Older planes, you got to turn them on and off and that. Everything else you can see. Bus ties, so left generator feeds AC bus 1, right generator feeds AC bus 2. So here, if you look at these side by side, they kind of parallel each other. We've got a schematic over here. We've got our panel. Here's IDG1, integrated drive generator 1. That's left engine. IDG2 here. You can see they normally power their respective AC bus 1 and AC bus 2. AC bus 1, AC bus 2. As we continue to work our way down, you can see there's a spot for AC external power, also known as a GPU or ground power unit, that can feed through these contactors to bus 1 and bus 2. Here is bus 1, 2. They don't even show a way to control those contactors individually. When you don't have engines running, you push that button in to connect to GPU. If it senses power, the airplane's automatically going to send power where it needs to go. AC bus ties, there's a few of these bus tie contactors that can be controlled using this dial right here. Normally it's an auto, but if for some reason you need to disconnect the bus from the other side, you pop it to the open position, it trips the bus and separates them. We have an APU generator as well. Here's our APU generator. That, again, can feed into either main bus 1 or bus 2. That is the entire AC control panel for this airplane. It's about that big. The size is a little bit bigger than an index card. That same control panel on the 727 is about yay wide and about maybe 12 to 14 inches wide and about 18 inches tall. And has all kinds of gauges and switches and dials and everything else. Okay. The bottom half here, this is DC power. That's everything down here. Here's our TRUs. There's the dividing line between AC and DC. This is all the bottom panel. Oh, I got arrows, so when you look at this at home, you can kind of see how these are all controlled. There we go. There's the 727 one I was talking about. 12 to 14 inches wide, 18 inches tall, got lots of switches. But at the end of the day, this schematic. This is just a schematic with actual physical switches, just like the other one was. Here is bus 1. Bus 1. Oh, here's the tie bus, the sync bus across the top. See how that line kind of goes from one panel to another? If these were all, they're 3 pieces, but this line, you can imagine it just continues all the way across. One solid bus, okay? That's your sync bus. Here's bus 3. There's the switch to turn on bus 3, bus tie breaker. There's the generator breaker. Basically your generators at the bottom, you control the frequency. This shows your current. This turns the generator on and off. This connects the generator to the bus. This connects the bus to the bus tie. And you can then connect anything, across the board. You'll learn to operate this out there. That turns the generator on and off. And like I said, down here, we can adjust frequency. And that's the same across the board. So here's bus 2, bus tie breaker for bus 2, bus tie breaker for bus 2. You can see how this is just a schematic that you can actually manipulate with some switches. Remember in there earlier, we've got our ground power goes in right here. It's not shown here, but our ground power, you see this little black and yellow outline. There's a black and yellow panel right here. That's our ground power panel. So we have a plug. We go through that switch to our bus tie. We close our bus tie breakers to power bus 1, bus 2, and bus 3, and that powers up the entire airplane. You'll learn how to do that in your second lab. There's also indication. Now, older aircraft, this was the indication you had. You had some gauges for current. You had lights. These lights come on when the breaker is open. Right? Normal is everything's closed or everything's on. And when we get to indication, we'll talk about cockpit design and the fact that we don't want lights on when things are working normal. We want it to be dark, and then we get a light that lights up when something goes wrong or becomes abnormal to get our attention, get the flight crew's attention. So that's your indication there. For newer aircraft, it's going to be built into an ICAS system or an ECAM system, some kind of an electrical display. And we will pick up back here next time.